What's up, guys? Welcome back. This time we are going to analyze an half-wave rectifier circuit with inductive resistive load. So last time we have already analyzed an half-wave rectifier circuit with a resistive load. So let me share my screen. So here are. So this is the circuit which we are going to analyze. So this is the half wave. This is the sinusoidal AC source. And this time we have added inductance in series to resistor. So these are the shape. These are the waveform we are going to analyze with LTS spice. So I'm just going to give you quick reference for the theory. So this is the theory, resistive inductive load. And this is Kirchhoff's law. And this is for the current. This is for the life. This is for force response. This is natural response. So this is the impedance for the LR RL circuit, and this is the phase. So we are going to analyze this one. This is the example 3.2 from the same book, Power Electronics by Daniel Hart. So the question is, for the half-wave rectifier of figure 3.2a, which we have already seen here. So this figure, this circuit. So the given resistance is 100 ohm and inductance is 0.1 Henry. And since the voltage source has frequency 60 Hertz, and this is in radian, just omega, which is 2 pi multiplied by frequency, which is 377. We can calculate over here. So 2 multiply 60 multiply 3.14, which is this one, which is almost 377 radian per second. So here the peak voltage is given as 100 volt, and we need to determine an expression for the current in this circuit. And the average current, the RMS current, the power absorbed by the RL load, and finally we need to calculate the power factor. So here is the solution. So we can find this one. It's so simple. It's just a square root of RA square plus omega L square, which is equals to 106.9 ohm. This is impedance for the circuit. This is the phase, and this is for the omega t, which is in radian. And these are the equation, and they are finding 0.308 ampere as average current, and RMS current is 0.474 ampere, and the power absorbed by the resistor is 22.4 watt. And this is alternating method. which is same. They are just checking the values, and this is the power factor. Average power divided by apparent power, which apparent power is nothing. It's nothing but it's VRMS multiplied by IRMS, which is 0.67. So now we are going to find this solution. We are going to compare this solution with LTS spice solution. So let's go to LTS spice. So here I have already built circuit. So I have the sinusoidal voltage on the basis of that example requirement. The DC offset voltage is 0. We are assuming amplitude for that one is 100 volt and frequency is 60 hertz. And we are assuming the diode is ideal and the given resistance is 100 ohm and inductance is 0.1 ampere, 0.1 Henry. So let's go and run this circuit. I have already shown over here. This is current following in the output current because both are in series. So the current should be same in both R and L. So here, how much I have already divided by pi to get the average current, which is 0.294773 ampere or 294.773 milliampere. So this is the average one. So first, when we delete pi divided by pi, then we are getting the peak. This is the peak one. Actually, when we run the circuit, we are supposed to get the peak current, not average current. To get an average current, we need to divide the peak current by pi. So right now we have 0.926 amperes, which is peak current. And now we are going to divide by pi to get average current. So average current is 0.2948 amperes. Now we are going to compare this value to average value, which is already calculated in this example. So this is the average one. So they use this integral to find the average current. But with LTS spice, we are just going to measure that value. So they have calculated 0.308 amperes as average current flowing through the LR. So how much we have over here in LTS spice? We have almost 0.295, which is quite close to the calculated value for the average current. Because this is theoretical and we have like practical, and we are still assuming the diode is ideal, but in reality the diode is not ideal. Diode is consuming some kind of voltage over there. That's why there is some kind of difference, a little bit difference in average current compared to the calculated theoretical current. Now we are going to find the IRMS. So to find IRMS, we already have average current, which is this one. To find IRMS, we can go over here. We don't need two cursor. We just need one cursor. We can delete the divider pi. We are just we need the peak current And to get an IRMS, we are going to divide this by 2, because the half wave rectifier is the average is just half of the peak current. So that should be the IRMS. Let me use the calculator over here. So so 0. Maybe we can use 926.0505557 milliamperes to divide by 4 divided by 2. So we are getting 463.02785, which is almost in milliamperes. So to get in amperes, we are just dividing by 1000. So this should be almost 0.463, which is IRMS. Now we are going to compare this value to the calculator value. So here the calculator value is 0.474, which is quite close to the measured value. So here we have just like this value is slightly higher than the calculated value. I mean the measured value, like 0.463, and it has measured calculated value 0.74. Now we are going to find the powers. So powers, the average power is nothing but it's the square of IRMS current multiplied by R. So we are going to use the calculator. So we can use this value, or maybe we can just use. Oh, we have 0.462, 0.426. Yeah, we can square this one. Oh, my bad. 0.462. We can just use, I'm going to use my calculator. 0.462 square multiplied by 100, the resistance value. So we are getting 21.34. So we are getting 21. 0.462 multiplied by 0.462. Then we are multiplying this one with 100. So yeah, we are getting the average power consumed by the resistor is 21.344 watts. Now we are going to find the IRMS. I mean, we are going to find the power factor. To find a power factor, we are going to use this relation. So now this is divided by so 0.4. So 0.462 divided by 0.462 divide here. Now we are going to divide by 0.462 divided by 100 divided by square root of 2. So we are getting 0.6534 power factor. And here they have calculated 0.67, and I'm getting 0.6534. So which is quite close to the calculated value. Now we can put the cursor over here. So this is the output. This is the power consumed in resistor. So here we have this value. So for this one, we are going to divide by 2. So basically we are going to divide by 4, which is here. This is the average power consumed by the resistor, which is 21.4394. So we had before 0.462 square multiplied by 100. We have quite same. Yeah. So we can analyze this circuit with this one. So now we are going to look at the shape of each waveform due to the source, due to the diode, due to the resistor, and due to the inductor. So first I'm going to see the waveform created by the source. So here is the source. So the source is here. So this is the current. This is the current. This is just inverted because of the diode. When you put over here, this should be over here. This is showing in forward. So for the voltage, the input voltage, the source voltage is this one. So the voltage is almost 99.78, but over here we have like 100. This is the peak one. Now I'm going to see the waveform created by a resistor. Or maybe we can put over here the output. So look at the output. You see the output is exactly same over here. So this is the peak voltage. To get the average one, we are just dividing by pi. So we can get the average one, which is 31.5 volt. Now I'm going to compare this waveform with this book. The book has also waveform over here. So it doesn't look like same. I mean, it doesn't have same value because this is for this circuit and it doesn't have any value specified. But the waveform look should be similar. So we have already checked that one, the source voltage, which is like this one, and right now I'm seeing the output voltage, which is like this here. Here it's this one. We can also see the input current, I mean output current. So here we have the output current is the output current is just it's half rectifier here. We check out diagram. Now I'm going to see the VR. This is the VR. Oh, so this is the VR. The yellow one, that is the VR. We can compare VR over here. So here is the VR. We can also compare this one. Yeah, here. So this is the inductive, the red color. This is the voltage drop in inductance. You can measure that. So the peak voltage drop is almost 27.95. Now we are going to see the diode. Let me see over here what they have. They have voltage drop in diode. So we need to put one cursor here, one probe over here, another one over here. So this is the diode, the blue color, or maybe we can double here. So this is the diode voltage. So this is the diode voltage. So it's almost like negative. It should be negative because it's an inverting. So here it is starting from 0, goes down. It has peak over here, minus Vm, which is minus Vm. It's going over here, still 0 over here, and going back to Vm, minus Vm. So we have same here. We have Vm over here, which is almost 100, like minus 100. We can maintain over here. This should be good enough, 99.9, which is good enough for diagram. So we have already proved all waveform for this circuit. We have already analyzed, and we have calculated all these values, and we compared with this solution, and we are good to go. Yeah, hope you understand this video, and I would like to thank you for watching, and see you next time. I'm going to stop my sharing. And